Hi everyone. We're going to start chapter 8 now, and chapter 8 is about bonding. A lot of what we're going to do is covalent bonding. And so this first little introduction, we're not going to get any more than this on ionic bonds. So there's two types of bonds, ionic bonds and covalent bonds. And I don't really think of ionic bonds as bonds because they're not individual bonds, right? We've got ions held together by the attraction of positive and negative charges. So these are those Coulombic forces. So Coulombic attraction. And when we think of a sodium chloride compound, it's not one sodium ion and one chloride ion. It's a sodium ion with a whole bunch of chlorides around it, and all the chlorides with a whole bunch of sodiums around it. They're not individual. So and then we're going to do Lewis structures a little bit later. I probably will say this again then, but I'll repeat myself a few times. I don't really think drawing Lewis structures for ions or ionic compounds makes any sense whatsoever because they're not molecules. They're compounds, right? So it's not an individual sodium with an individual chloride. All right, so that's all we're going to have on ionic bonding. All the chapter 8 and chapter 9 are about bonding, and it's really covalent bonding that we're interested in here. In fact, I'm having you'll see in the schedule, we're skipping the part where there's calculations about lattice strengths and things like that. I just don't think that's good use of our time. All right, so covalent bonds. So covalent bonds, and this is, this is the same way we talked about it at the start of the semester, right? No different level yet. So covalent bonds are sharing of electrons in orbitals between the nuclei. And that's it, all right? So we're gonna, let's see if I can find the next sheet. There we go. Look at some figures from the book. And this is figure 8.1. And again, we skipped the chapter on thermochemistry. So we're going to talk about energy a little bit, but we're not going to do any energy calculations with this. All right, so this is a diagram showing the energy or the formation of a bond for hydrogen, H2. And you'll want to read through this section, but I'll try and talk you through it as well. I really miss that Orbitron. I mentioned that before. It no longer works because they're getting rid of uh, Macromedia Flash. Won't run anymore. It's eliminated as of this year. So I can't, and I searched the internet. I found some things, but nothing that could do quite what it could do. Anyway, I missed that diagram. I'll keep looking to see if maybe somebody just has a movie, a little movie clip to show a similar thing. But the idea here is that we've got two hydrogen atoms that are far apart, and they're not interacting at all. So they're so far apart. And when you bring them closer together, they start to interact. And then finally, we have a hydrogen molecule. And these little dots are supposed to represent that electron. We can call it an electron cloud. It's the orbitals, with the electron existing in it, like we talked about with quantum mechanics, right? And then finally, that optimum distance, the bond distance, where you've got the two nuclei that are positively charged and the electrons in the orbital that are negatively charged. And so these are just the right distance so that it's perfect for that particular molecule. And the way to look at that then is this potential energy diagram. So this is energy going up, and this is the distance between the hydrogen atoms. So when they're way out here, two hydrogen atoms by themselves not interacting, that's zero energy, okay? That's our definition of zero energy. And as they come together, it's more stable for them to form that bond. That's why it's a diatomic molecule, H2, and it's lower energy. So the potential energy has gone down to minus 458, and now it's the hydrogen H2 molecule. If you squeeze those nuclei closer together, there's a lot of resistance to that, right? Because they're positively charged, and you can't get them closer together, and the energy just goes shooting way up. And in fact, the molecule will sit and kind of vibrate down in this potential energy well, right? And so the minimum energy, that's the formation of a bond. And then this would be for the hydrogen molecule, the distance between the nuclei is 0.074 nanometers. I don't know if you can read that on that. You can read it in your book or in the handout. And that's what we defined as the bond length. So right there is the bond length, okay? And then separate atoms out here. All right, a couple of things from this that, again, we skipped the energy chapter, but we will do it at the start of Chem 114 most likely. But things to know about what this diagram tells us. So once we have a bond to form that molecule, you can see that then it takes energy to break those hydrogen atoms apart. And that 458, that is the bond energy then of a hydrogen molecule. So we haven't talked about exothermic and endothermic. We will later, but I'm going to include this here anyway. Formation of bonds is exothermic, and what that means is energy is released by the formation of this bond. Exo meaning going out of. So the molecule is lower energy than those separate atoms, right? And that's why it forms the bond. And that's what we mean then, that the bond energy is defined as how much energy it takes to split it back up. All right, so let's look at some of these values. And again, we're not doing the calculations, so you don't need to worry about the calculations, although they're not really too bad. But again, the bond energy, this is a table of bond energies from your book, and they're average bond energies for different molecules. So for instance, hydrogen here we have 432. What did it say on there? 458. That's interesting. It should be the same, shouldn't it? I'll have to look into that. From the same book, it ought to be the same. HF takes more energy to break that. Okay. HCl 427. So, but then there's some, and since we're not doing the calculations, I don't want to dwell on this, but carbon hydrogen, this 413, that's an average. Okay, average. There are lots of different carbon hydrogen bonds within an organic molecule depending on what other atoms are in the vicinity. So that's an average value that is useful. All right, so again, let's just rewrite the definition of bond energy. Energy required to break the bond. And it always takes energy to break a chemical bond, and you always get energy when you form the bond. All right, so that's just the definition, a few things there. It's always exothermic when you form the bond. And let's look at the next slide. So this is another table that has bond lengths and bond energies for a few of these bonds. So we need to define a couple of things, and this may make more sense after we start doing Lewis structures, but you know, we'll see. Hopefully it'll work for you. So the first thing I want to do is just define something called bond order. So when we draw the Lewis structures, we're going to represent how many covalent bonds there are between two atoms in the molecule. And so the bond order is just the name for the number of bonds between atoms. And we're always, there's ways of getting this from other things. We're always just going to get the bond order from the Lewis structure. That's the next topic after this little introduction. And then if you look at it, I want us to kind of remember and hopefully understand once we do the Lewis structures what happens as you change the number of bonds. And we're just doing this very qualitatively, right? But so you have a carbon-carbon, call it a single bond if there's just one pair of electrons between those two carbon atoms. If you add a second pair of electrons, that's now a double bond. And notice it gets shorter. Does it make sense to you that having two more electrons in between the nuclei pulls those nuclei closer together? Right? There's two bonds there now holding it together. And then if you go up to three bonds, which we call then a triple bond, makes sense, it pulls it even closer together. And does it also make sense to you that it's going to take more energy to pull it apart if there's a double bond or a triple bond? If you look at the bond energy, the average bond energy for a carbon-carbon bond, 347, it almost doubles, not quite doubles when you go to a double bond, and it doesn't quite triple, but it's still quite a bit stronger once you go to the triple bond. All right, so that's the idea, and this is just one of those, let's remember and kind of understand it conceptually, but as the bond order increases, that means the energy increases and the length decreases. It gets shorter. And that's worth remembering separately from your understanding of it, reciting with your bedtime prayers, something like that. All right, so let's see if I can find the next sheet. Oh, I'm supposed to do a bond order example. All right, let's do a bond order example. I'm just going to draw a Lewis structure without having done it, and then we will do more bond order examples once we've drawn some Lewis structures. So let's say we have this molecule, and again, maybe this will make more sense after we do the actual Lewis structures. I think a lot of times I'll do that in that order, but since we're not in class, I wanted this stuff in one video, Lewis structures in another video. So hopefully it'll work for you. This is a Lewis structure, and I'll explain those more in the Lewis structure video. But what it shows is each line, each dash is a pair of electrons. And it just represents, so the Lewis structure represents all the valence electrons in the molecule. And so when we look at this, that means there's a carbon-hydrogen single bond here, a carbon-hydrogen single bond. And this is the order in which they're all connected. This carbon's connected to that carbon, which is connected to two oxygens, and this oxygen has a hydrogen on it. These are lone pairs. We'll worry about that when we do Lewis structures. And so when we look at this, if we were looking at, say, just this piece of it, that carbon-hydrogen bond has a bond order of 1. And you just look at the Lewis structure and say, well, there's one bonding pair of electrons between it. That's a bond order of 1. So we don't have to go through and do all the other stuff that they might have you do in chapter 9 and when we do molecular orbital theory and stuff like that. We're always just going to get it off of a Lewis structure. And then if you look at here, well, what would that carbon oxygen be? Well, there's 2 pairs of electrons there, so that has a bond order of 2. All right, not too bad, right? You can definitely do bond orders based on that. And that bond order of 2, then we call that a double bond, and we have the energy, average energy of that on the previous one. So hopefully that makes sense. And then we'll come back when we do resonance structures, we'll talk about bond orders that are in between 1 and 2 or 3 or whatever they happen to be. All right, so let's see. I forgot I was going to stop saying so. This is a figure from your book, figure 8.12. It'll come across much better on screen or in the handout. But what we want to talk about here is electronegativity and just how these electrons are shared in an atom. So we defined, I defined electronegativity. I don't know why I used the royal we in the world. Electronegativity, we talked about that. I talked about it. I think it's because normally people are there and I say we're talking about it together. Maybe there's questions. Anyway, enough jabbering. Electronegativity. I defined it in the last chapter because I wanted to do all the periodic trends together, right? And so electronegativity is the ability to attract electrons in a covalent bond. And so this shows, this figure 8.12, shows 3 possibilities here. I'm going to show the bottom one first. This is an ionic compound, and I don't even like this diagram, right? Because we don't have molecules of ions. Anyway, now I know there's a whole section in the chapter about percent ionic character, and it's not such a sharp line and all that kind of stuff, but nevertheless, let's keep it simple, right? Especially, you throw these in water and they're separate ions, so it's kind of irrelevant anyway, if they dissolve, that is. So forget about ionic compounds. This is a representation. They're just showing it's not, it's completely transferred, right? This is a cation, that's an anion, but remember, there's going to be a whole much more around there. So really what we're looking at are these top and bottom ones. And I know we can't see it there, so I'll write in F2 and HF, okay? And it's supposed to be showing the molecular orbitals that are formed when you form this molecule. And that's why I wish I could show you on the Orbitron. But they have really good pictures in the book, and you can see them a little here, but much better. So you got your 2 nuclei, and the electrons exist in an orbital around there with electron density between the 2 nuclei holding it together. And so since it's the same element, the same nucleus, fluorine and fluorine, that electron density is going to be evenly distributed all around there. So that is going to be non-polar, meaning it's the same on all sides, right? But if you have HF, well, fluorine is our most electronegative element. Hydrogen is not very electronegative. And so when these form a covalent bond, the electrons are pulled towards the fluorine. And this representation is really nice too. And a lot of times what we'll do is we'll draw it like this, and then we put this little delta minus by the fluorine and delta plus, just like they've done here, showing that one side of the molecule is more negatively charged, one side of the molecule is more positively charged, and there's a vector then showing which way that charge is going. And this shows kind of what the orbital would look like. The electron density is just more on that fluorine side. So that's a polar molecule. And it just means, just like north and south pole or ends of a battery, positive and negative, right? It's not full charges like an ionic compound. It's just leaning that way somewhat. And so you have a polar molecule and a nonpolar molecule. When we get to bigger molecules and do geometries and all that, we'll talk about polar molecules again. All right. Last thing in the introduction then, and maybe I should have done this first, the electronegativity, but since we already did it, this is kind of review, right? And so I think I need the marker for this one. Make it show up on the gray. So again, fluorine is the champion, and these values, I should probably now, since I didn't do this before, talk a little bit about where these values come from. They're made up. Okay, so I want to stress that, because when we did the other things, size of an atom, those are physical measurements that we made. And ionization energy, that's physically measured. We can measure that. Electronegativity is purely a human concept that we invented so that we can do some stuff and understand things a little bit better, right? It's not a real physical thing. All right, it's something we've invented in order to try and understand how molecules look. And so this Pauling electronegativity scale is based on some other things, and then they calculate it, and here we go. I do, hopefully none of the other chemistry teachers will see this, but I also, I'm a bit of a heretic. I just think electronegativities of the metals are irrelevant to Gen Chem anyway. There may be some things they use them for in some more advanced chemistry, but we're only interested in covalent bonding and polar molecules. Metal atoms do not form covalent. These are not covalent molecules, right? Our rule that metals plus nonmetals, that makes an ionic compound, that's still the best way to predict this. Okay, and so we're still going with that. When we do this chapter, ionic is metal plus nonmetal, just like we did back in chapter 2, and covalent is when we have nonmetal plus nonmetal. And I know that there's probably some of you that had to do this in high school, where you took the electronegativity difference, and if it was bigger than a certain value, you said that's ionic, and if it was smaller than a certain value, you said that would be covalent. And I don't want to belabor this or go into it too much, but it turns out that that doesn't work any better than saying if you have a metal plus a nonmetal, it's ionic, and you have a nonmetal plus a nonmetal, it's covalent. There's all kinds of examples where you can show a bigger electronegativity difference and it's still covalent, and vice versa. So because of that, if it doesn't work any better, plus, who has a table of electronegativity values walking around with them? To me, it's just not a very useful thing. So that means the electronegativities of the metals are kind of irrelevant to Gen Chem, because what are we going to do? We're going to talk about covalent molecules, not ionic compounds. All right, so that's just my not so humble opinion. So we could do some example, looking at this. You're not gonna have the numbers in front of you. So when you figure out, or you're asked whether a bond is polar or not, if you have two different nonmetals, we're going to say that's a polar bond. Now, it might not be super polar, but it's somewhat polar. So even, and there's other things that go into this too, such as lone pairs in the molecules. So it's not just the electronegativity value anyway. But if you look at, you know, I'm not going to give you one that I would call a Knight's move. Like when we do the periodic trends, I wouldn't give you a Knight's move to tell me, well, which is bigger, phosphorus or selenium? Well, you know, it's down, but it's over. So that's not a fair question. If it's the other way, arsenic versus sulfur, yeah, sulfur is more electronegative because it's closer to fluorine this way and closer to fluorine that way. Does that kind of make sense? I hope that makes sense. So a Knight's, you know, or something like this, phosphorus down to tellurium. That's not fair. Anyway, one important thing that I want you to know, because hydrogen's up here all by itself, is that I'm sorry. Believe it or not, that's my eye doctor. I don't know. Anyway, sorry for the distraction. I should have just let it buzz, but I'm very easily distracted. A carbon-hydrogen bond. This is really important. So put 50 stars by that. Is nonpolar. Okay. Carbon-hydrogen bonds are considered nonpolar. Don't worry about what and hydrogen, right, it doesn't fit in there for electronegativity in the trend. And don't worry about what the values are. It's just any carbon-hydrogen bond anywhere in the molecule, those are nonpolar. All right, where's a blank sheet of paper? I'll do it on here. What if we had carbon fluorine, carbon oxygen, which is more polar? Maybe this is too easy, but it's good to do anyway. So which would be more polar? So when you look at this, there. Mother, you know, necessity is the mother of invention. I'm stuttering now too. Oh well. Fluorine's here, carbon's here. So 1, 2, 3 steps over. Carbon to oxygen is 1, 2. So they're farther apart in the trend, right? And so carbon fluorine is a more polar bond than just carbon oxygen. Carbon oxygen is also polar. But so I'm not, like I said before, I'm not going to say phosphorus to tellurium versus silicon to, you know, something like that. It's got to be clear one way or the other. All right. I believe that is it for the introduction to bonding, and the next will just be all representation of with Lewis structures. All right, thanks.